Greetings of the day to all of you. Well, today is Friday, 13th January 2023, and I am going to deliver lecture number 8 in a series of lectures on electric drives. In the previous lecture, that's lecture number 7, I discussed about torque speed characteristics of a separately excited DC motor and DC shunt motor, and also we discussed about speed control of separately excited DC motor. Today we are going to discuss the torque speed characteristics and speed control of DC series motor. DC series motor. Let us first of all derive its torque speed characteristics. Now we know that, let me first of all draw the equivalent circuit diagram of a DC series motor. This is a DC series motor. This is the applied voltage V, this is the back EMF EB, and let us suppose the resistance is R. R is the resistance of the field winding, which is connected in series with the armature, as well as resistance of armature winding. So I can write here the total resistance R is equal to RA plus RF. That is, it is armature circuit resistance plus field resistance. Let us assume that the current flowing in the circuit is IA. Now we know that if you apply Kirchhoff's voltage law in this circuit, V is equal to EB plus IA RA, or IA into R. R is the total resistance. Call this equation as equation number 1. We also know that back EMF is equal to K phi into omega m. It is proportional to flux and the speed of the motor. We also know that torque T is equal to K phi into IA. These are the three very important equations which we already know. Now, in case of a series DC motor, or in case of a DC series motor, since the field winding is connected in series with the armature, the field winding is excited by armature current itself or by the load current. So that means the flux which is produced by field winding, that is field flux, is directly proportional to armature current, which is same as the field current because field is connected in series with the armature. Or we can say that the flux K is equal to, flux phi is equal to Kf into Ia, where Kf is the constant. So therefore, from equation 3, we can say that torque is equal to K into phi. What is phi? Phi is Kf into Ia. So it is Kf into Ia, and there is one Ia here. Ia into Ia is Ia square. So torque is equal to K into Kf into Ia square. This will give us armature current Ia, which is equal to under root of T divided by under root of K into Kf. Let us call this equation as equation 4. Also from equation 1, we know that V is equal to EB plus IAR. So we can write, so from equation 1, we know that V is equal to EB plus IAR. So what is back EMF? EB. EB is equal to V minus IA into R. Right? Now what is back EMF? Just few moments back, we from equation 3, we have found that EB is equal to K phi into omega m, which is equal to K. What is phi? Phi is Kf into Ia into omega m. So EB is equal to Kf Ia omega m. So substituting in this equation, so therefore EB, in place of EB, we will write this Kf Ia into speed, which is omega m, is equal to V minus Ia into R. So from this we can find this omega m, speed of the motor, that is given by V by K into Kf into Ia minus Ia R by Kf into Ia, right? So this is what we get. This is omega m. omega m is V by K, and this is your IA. Okay, so we can simplify it. Omega m will come out to be V divided by K into Kf into IA. From equation 4, what is IA? IA is root T by root of K by Kf. So it is root 2, and this root of K into Kf, it will go up, right? Minus IA and IA goes, so it is R divided by K into Kf. If you rationalize it, you divide and multiply numerator and denominator by under root of K into Kf. What you will get? You will get speed is equal to V by under root of K into, it is V by under root of K into Kf into under root of T minus R divided by K into Kf. So this is the final equation for speed of a DC series motor. Okay, so from this equation you can very clearly find that speed is directly proportional to the applied voltage, and it is also, inversely proportional to flux, the flux represented by this constant Kf, and it is also inversely proportional to square root of torque, which means for no load, when the motor is on no load, what is torque? Torque is equal to 0. So therefore, what is speed? Speed is infinite. So because V by 0 is infinity. So for no load, the speed of the motor is infinite. And you can very clearly see that as the torque increases, the speed decreases. Speed is inversely proportional to square root of torque. As torque increases, the speed decreases as square root of torque. So therefore, if you plot the torque and speed characteristics of the DC series motor, the torque speed characteristics will look like this. This is torque and this is the speed. It will look like this. This is the torque speed characteristic of a series DC motor or DC series motor. At 0 torque, when torque is 0, speed is almost infinity. Then as you increase the load on the motor, the torque increases and speed decreases as per this equation. Now you have to understand a few points from here. So as torque increases, speed decreases. So you can see as torque increases, speed decreases. Now you have to understand a few points here. The question is, when the torque increases, when the load increases, why does the speed decrease? It has to decrease to maintain the balance between the applied voltage and back EMF. For example, if this is our DC series motor, this is the applied voltage V, and this is the back EMF EB. In order to make current to flow like this, IA, V should be always greater than EB. V should be greater than EB. That is the applied voltage, applied DC voltage should be greater than back EMF for the motoring operation. So in that case, when E is greater than EB, current is injected into the motor terminal, motor winding, current flows in this direction. Okay, so V has to be greater than EB. Now what happens when when the torque on the motor increases? See, when the torque on the motor increases, so as torque increases, increase in torque means increase in armature current, because when the load increases, that means the current drawn by motor from the source increases. So armature current increases. Since phi, the flux produced by field winding, is directly proportional to this armature current, so the field flux increases. And when field flux increases, back EMF increases. So since IA increases, flux increases, back EMF increases. And when back EMF increases, it may so happen that EB is greater than V. And when back EMF is greater than V, no current can come from the source. The motor will not be able to draw power from the source, because current will flow only when V is greater than EB. So therefore, in order to maintain the balance between EB and V, that means to make always V greater than EB in motoring mode of operation, right? What the motor will do, there will be a self-regulatory action. The self-regulating action will automatically decrease the speed of the motor. when speed of the motor decreases. So omega m, speed of the motor decreases. And since we know back EMF is directly proportional to speed, as speed decreases, back EMF decreases, thus making EB less than V, or in other words, V greater than EB. So the sequence of events is like this. When you increase the load, mechanical load on the motor torque increases. As motor torque increases, the current drawn by motor from the source increases. Since flux is directly proportional to armature current, flux increases. And since EB is proportional to flux, EB increases, it may make EB greater than V, and hence motoring operation will not take place. So in order to keep V always greater than EB in the motoring mode of operation, there is self-regulating action. What will happen to the speed of the motor? The motor speed will automatically decrease. When motor speed decreases, the back EMF also decreases, because back EMF is directly proportional to speed. And when back EMF decreases, the increase in back EMF on account of increase in load torque will be offset by decrease of back EMF by decrease of the speed. So when back EMF decreases, EB becomes less than V, or automatically V becomes greater than E, and hence motoring mode of operation always takes place. So therefore, in order to maintain the balance between applied voltage V and back EMF EB of the motor, omega m, that's the speed of the motor, should decrease with increase in the load torque. So that is why when the torque on the motor increases, the speed decreases like this. Okay, so I hope this is clear. One more very important point that you must know, that at no load or at light load, what is the speed of the motor? The speed of the, at no load, the speed of motor theoretically is infinity, infinite, a very huge speed, very high speed. So speed tends to infinity. So it is extremely high. It may be so high that the motor will lose the mechanical strength. Because of this huge centrifugal forces, the windings may come out of the slots of the armature, right? So therefore, it is advisable that the DC series motor should never be started on no load or on light load. It should be always started at some load. So this means DC series motor should always be started under some load. The question is, how much can be the no load speed? No load speed, because of the high mechanical strength of DC machines, the no load speed can be as high as 2 times the rated speed, but not more than 2 times the rated speed. Therefore, some mechanical load should always be connected or coupled to the DC motor, and so that when you start the motor, it is not started under no load conditions, because at no load conditions, speed tends to be infinite. It will cause mechanical damage to the motor. So motor should always be started with some load. In such a way, the load should be such that the no load speed does not cross 2 times the rated speed, because up to 2 times rated speed it is acceptable. So this is one very important point, which signifies that a DC series motor should never be started on no load or light load. It should always be started under some load conditions. Okay. So second very important point is that at torque overload, if you overload the motor, I will write at torque overload. When you overload the motor, the torque of the motor increases. Okay. The torque increases. That causes increase in the armature current, which causes increase in the flux, because field winding is excited by the armature current, which causes increase in the back EMF. So back EMF increases. So when the back EMF increases, what happens? IA, back EMF, opposes the flow of current, because what is this current, armature current? It is V minus EB by R. So when back EMF increases, when there is overload on the motor, torque overload, the armature current may become very, very large, very huge. But what happens when the armature current increases, the flux increases, that increases the back EMF. So back EMF increases, so armature current, which earlier temporarily had increased, it will come back, it will be maintained within safe limits. So therefore, under torque overload conditions. Torque overload conditions, we can say the armature current IA is kept within safe limits. Safe limits. This is not the case with separately excited DC motor, because in separately excited DC motor, if there is torque overload, the armature current will be drastically very large because back EMF will not increase. Back EMF, when there is overload, back EMF will not increase because field winding is separately excited. Flux is constant. Back EMF will remain same. In fact, due to the torque overload, the motor speed will decrease, back EMF will further decrease, and there will be huge increase in the armature current. So therefore, torque overload is not permissible in separately excited DC motor and also in DC shunt motor. However, torque overload to some extent is allowed in DC series motor. It can tolerate overloads because under torque overload conditions, the armature current is kept within safe limits. And let me tell you, at very high overloads, the magnetic saturation of the field winding or field circuit takes place, and the speed torque characteristic, which is like this, almost parabolic in nature, it will almost become a straight line. So this tells us that there is the possibility of overload or torque overload in a DC series motor. It is possible to have to use the DC series motor under overload conditions also, because under torque overload conditions the armature current is kept within the safe limits. The question is, that's about torque speed characteristics of DC series motor, and why does a DC series motor find its applications? One of the significant characteristics or one of the significant features of DC series motor is that it develops a very high starting torque. For example, at standstill, speed is zero. What is torque? Torque is very, very large. It develops a very huge starting torque. The starting torque developed by a DC series motor is very large. Starting torque is very large. So therefore, it is suitable for those applications where large or heavy starting torque is required. Example is an electric train or traction. So one of the examples is electric traction. Because in case of electric traction, when you start a train, you have to start it against huge friction torque. So it requires large starting torque. So DC series motor is most suitable motor for starting an electric traction. So it finds applications in electric traction, and also it finds its applications in those loads where frequent starts and stops are there. Frequent starts. Okay. So in those conditions, in those types of loads where heavy starting torque is required and the motor needs to be frequently started and stopped, DC series motor is the best motor for such applications, especially for those applications where large starting torque requirement is there, like electric traction. Now let us quickly come to speed control techniques of DC series motor. The same speed control techniques which we have studied for separately excited DC motor, the same speed control techniques are applicable for DC series motor. What is the first technique? First technique is armature resistance control. Armature resistance control technique. So in armature resistance control technique, this is our DC series motor. This is the field winding. An external resistance R is put in series with the armature circuit. This is the applied voltage V, and this is armature current IA, and this is the back EMF of motor EB, right? So when you put resistance in series with the armature, the speed decreases, because just few moments back we have derived the expression for speed of DC motor. What is the speed of DC motor? It is V divided by under root of K into KF into under root of T minus R divided by K into KF. So when you change R by putting variable external resistance, this is a variable or controllable external resistance. When you change R, the speed also gets controlled. So therefore, if you draw the torque speed characteristics under this condition, the torque speed characteristics will be like this. This is the torque speed characteristic for R equal to R1. Say rated torque speed characteristic, where R1 is equal to the internal armature winding resistance. If you increase the, if you put external resistance in series with the armature circuit, say R2, then what will happen? As per this equation, you will get reduced speed, because this will increase. When you increase R, this will increase. So omega m is this minus this, so omega m will decrease. So this is for R equal to R2. Similarly, if you further increase external resistance, you'll get R3 and R4, where R4 is greater than R3, greater than R2, greater than R1. So if this is the load, let us say this is the load torque TL. For R equal to R1, what is the speed of the motor? Omega m1. For equal to R equal to R2, it is omega m2. For R equal to R3, it is omega m3. For R equal to R4, it is omega m4. So R4 is greater than R3, greater than R2, greater than R1, such that omega m4 is less than omega m3, less than omega m2, less than omega m1. And hence, by changing or by controlling the external resistance in series with the armature circuit, different torque speed characteristics can be obtained like this, and we can have a wide range of speed control. By varying R, omega m can be controlled or it can be changed. So although this method is one of the simplest methods of controlling the speed of a DC series motor, but it's a highly inefficient method. The drawback is that it is a highly inefficient method of speed control. Inefficient method of speed control due to large Ia square R loss in the resistance. When you put external rheostat or resistance in series, it carries the full load motor current IA, and there will be large Ia square R loss, and hence efficiency of this method is very, very poor. Okay, so that's why this method is not very popular. Second method is armature voltage control technique. Armature voltage control technique. Again, I will write the mathematical expression for speed of the motor. Omega m is V by under root of K into Kf to under root of T minus R divided by K into Kf. So speed is directly proportional to applied DC voltage. As V is controlled, omega m gets controlled. So therefore, speed of DC series motor can be directly controlled by controlling the applied DC voltage. So that means if this is our DC series motor, this is the back EMF EB, this is the field winding, and the total armature plus field winding resistance is R. This is the applied voltage. There is no external resistance connected. This is the applied voltage and this is the armature current. This applied voltage we control with the help of maybe a chopper or phase controlled converter. A controlled DC voltage is applied across the armature terminals, and since V is controlled, omega m gets controlled, and you will get this type of torque speed characteristics. This is torque axis and this is omega m speed axis. This is, say, for V equal to V1, this may be rated voltage. Then this torque speed characteristic for V equal to V2, this is for V equal to V3, and this may be for V equal to V4. Let us suppose this is the load torque, this is TL. So therefore, for V equal to V1, this is the speed of the motor, omega m1. When you reduce, see, in this direction, you are reducing the voltage. V is reduced. Okay, you are reducing the voltage. So you get parallel torque speed characteristics. For rated voltage V equal to V1, the motor runs at speed omega m1. When you reduce the voltage from V1 to V2, this is the operating point, and motor runs at reduced speed omega m2, which is less than omega m1. At V equal to V3, the speed is omega m3. At V equal to V4, the speed is omega m4. So therefore, V4 is less than V3, less than V2, less than V1, and hence omega m4 is less than omega m3, less than omega m2 less than omega m1. So that means as the applied voltage is reduced, the speed also gets reduced. Okay, so this is how we can achieve speed control by armature voltage control method. The advantage of this method is that this is efficient method of speed control, because we are not wasting power in any resistance. We don't have any external resistance in series with the armature circuit. So this is highly efficient method of speed control. Now the two methods of speed control which we have already discussed, armature resistance control technique and armature voltage control technique, they give speeds below base speed. This is the base speed, rated speed at rated voltage, and you know, if you reduce the voltage, you get the speeds less than base speed. Similarly, in the armature resistance control method, you have seen that when armature resistance is increased, you get speeds less than base speed. Now, if you want to get speeds above base speed, you have to use the third speed control technique. That is field control method or flux control method. In field control technique, what we do, this is the motor as usual, motor armature back EMF, this is armature current IA, this is the field winding, series field winding, this is the applied voltage. Now we will want to control the current through the field winding IF. What we will do, we will connect a diverter resistor. This is RD, variable resistor. It's called diverter resistance. The current through this diverter resistance RD. When IA reaches this point, it gets divided. Some of the current flows through the diverter resistance RDs and some current flows through the field. By reducing this diverter resistance, ID can be increased and IF can be reduced. So if diverter resistance is removed, IF will be equal to rated field current and you will get base speed. But when you put diverter resistance across the field winding, some current gets diverted through the diverter resistance and IF reduces. And when IF field current reduces, that means flux reduces. Flux becomes less than rated flux. And when flux reduces, the speed will increase because speed is inversely proportional to field flux. Omega m is equal to V divided by under root of K into Kf into under root of T minus R by K into Kf. Field flux is represented by this factor Kf. So as field current is reduced, flux reduces, and as flux reduces, that means Kf is reduced. What will happen to speed? Speed will increase. It will become greater than base speed. I can show on the same characteristic. This is the torque speed characteristic for phi equal to phi. This is say for phi equal to phi 1 rated torque speed characteristic. This is for phi equal to phi 2. I mean phi 2 is less than phi 1. This is for phi equal to phi 3. This is for phi equal to phi 4. So what we are doing, we are reducing the flux in this direction. And as flux is reduced, the speed increases. So I can write that phi 4, field flux phi 4 is less than flux phi 3, less than flux phi 2, less than flux phi 1. And what about the speed? If you see the speeds, let us assume this is the torque, load torque. At phi 4, speed is omega m4. At phi 3, speed is omega m3. I can show it separately on a separate graph. To avoid any confusion, let me draw it again. This is the torque speed characteristic for phi equal to phi 1 rated. This is phi 2, phi 3, and phi 4. And if this is the load torque TL, for phi equal to phi 1, the speed is omega m1. For phi equal to phi 2, the speed is omega m2, which is greater than omega m1. Then this is omega m3 and this is omega m4. So in this direction, what you are doing, you are reducing the flux. As flux is reduced, speed increases and you get speeds above base speed. This may be base, the torque speed characteristic corresponding to base speed. This is more than base speed, more than base speed, more than base speed. So phi 4 less than phi 3, less than phi 2, less than phi 1. So omega m4 is greater than omega m3, greater than omega m2, greater than omega m1. So that means as the flux is reduced, speed increases. So you get speeds above base speed. Okay, so therefore flux control method or field control technique is used for achieving the speeds above base speed. So this is about DC series motor, various methods of speed control. That's it. That's all about DC series motor. So in this lecture, what we have done, we have derived the torque speed characteristics of DC series motor mathematically, and we have plotted those torque speed characteristics. We have seen the torque speed characteristics are such that as torque increases, the speed decreases. Okay, speed decreases as square root of torque. And we have seen that the question is why speed decreases, because as torque increases, field flux increases, because in series motor, field is in series with the armature. Increase in torque means increase in armature current. Increase in armature current means increase in field flux, which means increase in back EMF. Hence, the speed of the motor has to decrease in order to keep back EMF always less than applied voltage, so that the motoring operation takes place. That's why in a DC series motor, when torque increases, the speed decreases. In fact, speed decreases as square root of the torque. And then we have seen that this DC series motor should never be started under light load or no load conditions, because at no load conditions, a dangerously high speed is resulted in, which may cause mechanical damage to the motor. So therefore, it is recommended that a DC series motor should always be started under some load conditions. And we have also seen that this motor is suitable for torque overload conditions, because for torque overload conditions, as torque overload takes place, IA increases, phi increases, EB increases, so IA is kept within safe limits. Torque overload does not mean armature current overload. The current drawn by motor from the source does not increase appreciably. It is kept within safe limits. And then we have seen its applications. It's used in those applications where high starting torque requirements are there, like electric traction. And then we have studied about different methods of speed control of a DC series motor. Armature resistance control method, which is inefficient method of speed control due to high I square R loss. Then armature voltage control method, which is an efficient method of speed control, and field control technique. Out of these control techniques, the first two, that's armature resistance control technique and armature voltage control technique, give speeds below base speed. And the third technique, that's the field control technique, gives speeds above base speed. That's all about DC series motor. Let us try to solve a numerical problem. This is the numerical problem. This is for a separately excited DC motor that we have studied in previous lecture. I will read the problem for you. The problem says a 230 volt 500 rpm 100 ampere separately excited DC motor has an armature resistance of 0.1 ohm. The motor is driving under rated conditions a load whose torque is constant and independent of speed. The speeds below the rated speed are obtained with armature voltage control with full field, and the speeds above rated speed are obtained by field control with rated armature voltage. Part A. Calculate the motor terminal voltage when rated speed is 400 rpm. Part B. By what amount should the flux be reduced to get a motor speed of 800 rpm? Neglect the motor's rotational losses. I will take this paper close to your camera so that all of you can note down this numerical problem. Okay, you can pause the video for some time and note down this numerical problem. Let's try to solve this very interesting numerical problem. So this is the example. We'll try to solve it. The data is given is a separately excited DC motor like this. We have a separately excited DC motor. This is the armature resistance RA. It's given in the problem that armature resistance is 0.1 ohm. Applied voltage is 230 volts. Armature resistance is 0.1 ohm. It includes the resistance of brushes also. And this is the field winding with field resistance, variable field resistance RF. And this is the field voltage VF, field current IF. Okay, armature current is IA. It is given in the problem 230 volt. That means input DC voltage is 230 volts. We'll write the data. V is equal to 30 volts, 500 rpm. That was the speed of the motor. N1, original speed is 500 rpm. 100 ampere. That means armature current is 100 amperes. Under full load conditions, it draws a current of 100 amperes. Separately excited DC motor has an armature resistance of 0.1 ohm. Ra is given as 0.1 ohm. The motor is driving under rated conditions a load whose torque is constant. So it is driving a constant torque load and independent of speed. Obviously, constant torque load is load has a torque which is independent of speed. The speeds below rated speed are obtained. If you want speeds below rated speed, below base speed, which method will you use? Armature voltage control with full field. That means field current is constant. And the speeds above rated speed are obtained by field control method. This we already know. When you use field control method, at that time rated armature voltage should be applied. Part A, calculate the motor terminal voltage when the rated speed is 400 RPM. I mean, you have to reduce in part A the speed from 500 RPM to 400 RPM. So N2 is 400 RPM. In part A, you have to use the voltage control method. I will write here voltage control method. In order to reduce the speed from 500 RPM to 400 RPM, you have to reduce the applied voltage because you are using the voltage control method. The question is, what should be the applied voltage? For 500 RPM speed, applied voltage is 230 volts. For achieving 400 RPM speed, what should be the applied voltage? Obviously, it should be less than 230 volts. How much? Let us try to find out that. We know that the speed of motor is equal to, or let's write like this. We know that back EMF is given by K phi omega m, or we can write K phi n. EB1, originally when the motor is running at 500 RPM, at that time, whatever is the back EMF, let's call that EB1, is equal to K phi N1. Okay. Flux you have to maintain constant. So K into phi is constant. N1 is the speed, RP. Let's call this equation as equation 1. And when you are running the motor at 400 RPM, at that time back EMF will change. Let's call that back EMF as EB2. That will be equal to K phi because flux is constant into N2. Dividing equation 1 by equation 2, you will get, or dividing equation 2 by equation 1, you will get EB2 by EB1 is equal to K phi N2 by K phi N1. K phi and K phi goes. So this will give you EB2 is equal to EB1 times N2 by N1. Let us try to find out this. So that means the new back EMF at reduced speed is equal to original back EMF. What is original back EMF? We have to find it. Let's write EB1 into N2 by N1. Call this equation as equation 1. Now we know that V is equal to EB1. V1 is equal to EB1 plus IA R. Okay. So V1 is the applied voltage, 230 volts, is equal to, from this we can find EB1. So EB1 is equal to V1 minus IA into RA. So I into RA. V1 is the applied voltage, 230, minus IA is the armature current. It is given in the problem. 100 into armature resistance is 0.1 ohm. So it is 230 minus 10. That is 220 volts. So back EMF is 220 volts. So substitute here EB1. So therefore, you will get EB2. Therefore, EB2, new back EMF at reduced speed of 400 RPM will be back EMF at 500 RPM. We have found that that is 220 volts into N2. N2 is the new speed, reduced speed. How much is that? N2 is 400 divided by N1. N1 is the original speed. It's 500. So 220 into 400 by 500. So I have calculated it. It will give EB2 equal to 176 volts. At 500 RPM, the back EMF is 220 volts. At reduced speed of 400 RPM, the back EMF obviously also reduces. It reduces from 220 volts to 176 volts. So therefore, what is the applied voltage? Therefore, V2 is equal to EB2 plus IA into R. IA into RA. IA will remain constant because we have a constant torque load. A constant torque load always draws a constant armature current. So therefore V2 is equal to EB2. EB2 is 176 plus IA 100 into RA is 0.1. So V2 is equal to, I have calculated it, let me give you the values. EB2 is equal to, right, how much is this? I have already calculated 176 plus 10, because 100, this is 176 plus 10. So V2 is equal to 186 volts. That's it. This is part 1. In part A, you have to find the applied voltage. At 230 volts rated voltage, the motor runs at 500 RPM. What is the applied voltage if you want to reduce the motor speed from 500 RPM to 400 RPM? The new applied voltage should be 186 volts. Therefore, if you reduce the voltage from 230 volts to 186 volts, the motor speed will reduce from 500 RPM to 400 RPM. That's it. That is about part A. Let us try to find out part B. In part B, you have to use the field control method and you have to get the speeds above base speed, because in part B, it is said by what amount should the flux be reduced to get a motor speed of 800 RPM. Now you have to get a new motor speed N2 equal to 800 RPM. Or let us call this N3 equal to 800 RPM. You have to get the new motor speed. So for getting, this is the speed above base speed, because base speed is 500 RPM. So obviously, in order to get speed above base speed, you have to reduce the field current, field flux. So in the question, it is asked by what amount should the flux be reduced to get this new speed. Now, in order to solve this problem, uh, let us write here, let new flux be, you have to reduce the flux. Let new flux be phi 2 equal to k times phi 1. So therefore, we will try to find out this k. Okay. Let phi 2 be equal to k times phi 1. Let's call this equation as equation 1. And since we know that back EMF EB is equal to, it's given by k phi omega m, okay, omega m3. And what is omega m3? Omega m, so we can write, let's call this EB3. EB3 is equal to k, now it should be phi 2, k into phi 2 uh, into, what is omega m3? Speed is given in, omega m3 is the speed in radians per second, but n3 is speed in RPM. So it is RPM. If you want to convert speed from RPM to radians per second, you have to multiply it by 2 pi by 60. Okay, so this will give you speed in radians per second. So EB3 will come out to be, it comes out to be, I have calculated it, let me give you the value. EB3 comes out to be k phi 2, okay, it is k phi 2 into 83.8, because this 800 into 2 pi by 60 is 83.8 radians per second. Okay. So this is EB3. Now this this is phi 2. What is phi 2? Phi 2 is k into phi 1. Let's call this kc into phi 1. So EB3 is equal to k kc phi 1 into 83.8. So it is 83.8. Okay. Now we know that EB is equal to k phi omega m. Let us try to find out this kc. Okay, it is k phi omega m, और k phi का value हम निकालने की कोशिश करेंगे. We will try to find out this k phi. So what is this k phi? It is EB by omega m. Okay, so EB is 220 volts, because applied voltage is 230 volts. Just few moments back in part A, we have found EB1. EB1 is 220 volts. EB1 is basically V minus IARA. V is 230 volts minus IA is 100 into RA is zero point 0.1. So 230 minus 10 is 220 volts by omega m. And what is omega m? Omega m is 52.4 because omega m is, see, your speed, original speed of motor is 500 rpm. So omega m will be 500 into 2 pi by 60. If you calculate this, it is 500 into 2 pi by 60. That comes out to be 500 into 2 pi by 52.5, sorry, 52.4 radians per second. That's what I am substituting here. So 220 by 52.4, it comes out to be 4.2. And therefore this k into phi I can substitute here. K into phi from the previous part comes out to be 4.2. So therefore EB3 will be equal to Kc into K into phi. What is K into phi? K into phi is 4.2 into 83.8. So let us simplify it. This is 83.8. So EB3 comes out to be 351.9 K. Let us call this equation as equation 2, right? Now we can also write, I can write this EB3 equal to 351.9 K here. This is equation 2. We also know that torque is given by, Kc phi into Ia, right? So Kc phi into Ia is equal to phi 1 into Ia1 is equal to Kc K phi 2 Ia2. Okay. So from this, Ia2 is equal to Kc by what is this? Okay, this is K here. This is also K. K. So the K and K cancels. So Ia2 is equal to phi 1 by phi 2 into Ia1. Okay. What is phi 1 by phi 2? Here in equation 1, phi 2 is K times phi 1. It is K times phi 1, right? We already know it is K times. So from this, what is phi 2 by phi 1? Or phi 1 by phi 2 is equal to 1 by K. So therefore, phi 1 by phi 2 is 1 by K into how much is the armature current? 100. Okay. So this is 100 by K, Ia2. Now what is V? What is the applied voltage? Applied voltage should remain constant. V is equal to EB3 plus Ia2R2, Ra2. Okay, or Ia2Ra, because armature resistance is also constant. So applied voltage should remain constant. So 230 is equal to EB3. What is EB3? EB3 we will write as like this, plus Ia2 you have found, it is 100 by K into what is armature resistance? 0.1. So 230 is equal to EB3 plus 100 into 0.1 is 10. So it is 10 by K plus 10 by K. Ia2 into R2. Ia2 is 100 by K, okay, into Ra2. So 230 is equal to EB3. Hold on, there is some mistake somewhere. Ia2 is 100 by K. V is E plus Ia2R. 230 is E3 plus, it is 0.1 Ia2. It is 0.1 Ia2. It is 0.1 IA2. IA2, let's keep it as IA2 itself. 0.1 IA2 because RA is 0.1, right? So it is 0.1 IA2. So therefore we can substitute EB3 we have already found in some equation. Just few moments back we have found out EB2, how much was EB3, sorry. EB3 just few moments back we have found EB3 is 351.9 K. We have found it just few moments back. Okay. So we can therefore we can write 230 is equal to EB3. EB3 is 351.9 K plus 0.1 into IA2. So 230 is equal to 351.9 K plus 0.1 into IA2. IA2 is, what is IA2? IA2 is 100 by K. IA2 is 100 by K. You can substitute now 100 by K. So this will give you EA2 or 230 equal to 351.9 K plus 10 by K, right? So this will become a quadratic equation. See, 351.9 K square minus 230 K plus 10 is equal to 0. If you solve this, it will become a quadratic equation. Solve this quadratic equation. K is minus B. Minus B is 230 plus minus under root of B square. B square minus 4AC. A is 351.9 into C. C is 10. Whole divided by 2A. 2 into 351.9. So when you solve this quadratic equation, it is K equal to minus B plus minus under root of B square minus 4AC by 2A. So this will give two different values of K. So I have calculated it. K is 0.61 and 0.05. 0.61 and 0.05. So the most reasonable value or feasible value of K is K equal to 0.61. That's it. And we already know what is K. Okay. What is phi 2 by phi 1? We had earlier we had written somewhere that phi 2 is equal to K times phi 1. If phi 1 is the rated flux, phi 2 you have to reduce in order to increase the speed from 500 rpm to 800 rpm. So by what amount are you reducing this flux? By an amount of 0.61. So therefore phi 2 should be 0.61 times phi 1. So therefore by how much amount should we reduce flux? So therefore we can say that the flux must be reduced to 0.61 times 61 of its rated value to get a high speed. So therefore flux should be reduced to 0.61 of its rated value. That is phi 2 should be 0.61 times phi 1. So it should be 61% of phi 1 should be reduced to 0.61. When you reduce the flux by 0.61 of phi 1, you get higher speed. So you get higher speed N3 equal to 800 rpm. So your motor runs at a speed which is greater than base speed. So that's all in this numerical problem. In part A, we applied armature voltage control and we got a speed below base speed 400 rpm. And we were asked to find out what is the applied voltage for getting a reduced speed. For rated voltage of 230 volts, the speed is 500 rpm, and for getting 400 rpm, we found that this this applied voltage should be reduced to 186 volts. Okay, if you reduce it to 186 volts, you will get a speed of 400 rpm. That's part A. In part B, you are supposed to use the field control method. In the field control method, you get a higher speed, higher than base speed, 800 rpm. It was asked that in order to get 800 rpm, by how much amount should you reduce the flux? We solved the problem and we found that the flux should be reduced by 0.2, 0.61 of the rated flux in order to get a new speed, higher speed of 800 rpm. I hope this numerical problem will make things very much clear. Whatever we have learned in the previous class about speed control of separately excited DC motor, this numerical problem will aid you, help you in understanding those concepts. And in today's lecture, we developed the torque speed characteristics of a DC series motor, and we identified its application, and we also discussed about speed control techniques of DC series motor. So that's all in today's lecture. Thank you.